There are two types of chemical formulas that relate to the composition of a substance: empirical formulas and molecular formulas. An empirical formula represents the smallest ratio in that molecule or in that compound, compared to a molecular formula where the ratio is there, but it actually represents the number of atoms in that molecule or compound. Here's a few examples: water, hydrogen peroxide, ethylene, and sodium chloride. Let's compare the empirical and molecular formulas for these compounds. First off, water. The empirical formula for water is H2O. What about the molecular formula? That's also H2O. What about hydrogen peroxide? The empirical formula is the smallest ratio of the atoms in that compound or molecule. So in hydrogen peroxide, there are 2 hydrogens and 2 oxygens. That could be simplified to represent 1 hydrogen and 1 oxygen because it's a 1-to-1 ratio. But the molecular formula is H2O2. What about ethylene? There are 2 carbons and 4 hydrogens. This can also be simplified. 1 carbon and 2 hydrogens. I divide by 2 and I divide by 2 to give me 1 carbon and 2 hydrogens. But the molecular formula is still C2H4. What about sodium chloride? Sodium chloride is a 1-to-1 ratio. And so the molecular formula would be the same, but with ionic compounds, the empirical formula is what we use to represent them. Chemists prefer using molecular formulas because it has more information. Here's an example. Benzene, C6H6, compared to acetylene, C2H2. These are the molecular formulas, so that gives a lot of information. I know that there's 6 carbon and 6 hydrogen in benzene. Acetylene has 2 carbon and 2 hydrogen. If I only had the empirical formula, both the empirical formulas look the same, but these are 2 very different compounds. Here's an example problem for empirical formulas. I have a substance that consists of 5.88 grams hydrogen and 94.12 grams of oxygen. What is the empirical formula? It's asking for the empirical formula, and it gives me 2 bits of information. I need to convert these to moles, and then I can create my ratio to find out what my empirical formula is. So let's go ahead and start with hydrogen. 5.88 grams of hydrogen, and I'll write down oxygen also. 94.12 grams of oxygen. Let's convert to moles. I can use my mole map, and I know that I need to have the molar mass. What about oxygen? What do I get when I multiply that out with my calculator? Here, I get 5.8333. Here, I get 5.8825. Now my next step is to take the one that is smallest and divide everything by that number. Just a hint, looking at these, they are so close, it should be a 1-to-1 ratio, but let's divide anyway. 5.8333, I should get 1 there. Divide by 5.8333, and I get 1.00843. This can be rounded to this whole number of 1. So I know it's a 1-to-1 ratio. So my empirical formula will be HO. And that's my answer. The next question related to this problem is as follows. The actual compound has a mass of 34 grams per mole. What is the molecular formula? So we're looking for the molecular formula, and it gives us that information. So let's take our empirical formula and find out what mass that is. So I'm going to bring that down here. So here's my empirical formula. Look at the periodic table and find out what the molar mass of this is. Hydrogen is roughly 1. Oxygen is roughly 16. That's a total of 17 grams per mole. Let's compare this mass to this mass. Now, if you remember, Empirical formula and molecular formula differ or can differ. Empirical formula is the smallest ratio of those atoms in that molecule or compound, whereas the molecular formula can be the same as the empirical formula, but it is the representation of the actual amount of atoms in that molecule or compound. So here we know that this goes into 34 2 times. Let me just prove that to you. Multiply this by 2 and you get 34. That means that the empirical formula is not the same as the molecular formula in this case. The empirical formula must be multiplied by 2 so that we can get the molecular formula. So the molecular formula should be H2O2. And that is our answer. Let's just prove to ourselves that it has this mass. 2 hydrogens, a value of 2. 2 oxygens, a value of 32. Add those up, and you get 34. If we know the percent composition, instead of the actual masses, which we have dealt with before, we must convert the percent composition to relative masses before we actually calculate to moles. The simplest way is to use a hypothetical sample weight of exactly 100 grams. So we can say we have 73.19% carbon or 73.19 grams of carbon. So we'll start there. What about oxygen and hydrogen? Now we can convert into moles. Let's start with carbon. I know my ratio is 12.01 grams per mole of carbon. I get this from the periodic table. When I calculate that out, I get 6.094 moles of carbon. Let's do oxygen. I look at my periodic table and I know that there are 16 grams per mole of oxygen. I multiply that out and I get 1.218 moles of oxygen. And finally with hydrogen, I look at my periodic table and the value is 1.008 grams per mole of hydrogen. I multiply that out and I get 7.312 moles of hydrogen. What's my next step? My next step is to find the smallest amount of moles. That's my smallest amount. I divide everything by that amount. So I can find my ratio for my empirical formula. What do I get here? I get roughly 5. Here I get a value of 1, and here I get a value of 6. My empirical formula should be 5 carbon, 1 oxygen, and 6 hydrogen. That's my final answer. Notice that these are nice whole numbers. That won't always be the case. Let me show you an example. We are given percent compositions. So we know that we can convert those to a hypothetical 100 gram sample, so we can make these each grams. Let's start with carbon, and hydrogen, nitrogen, and oxygen. Let's go ahead and convert to moles now. I'll start with my carbon. And how many moles does that make? Next is hydrogen. Moles of hydrogen. Great. And next nitrogen. And finally oxygen. Now I need to find the smallest number and divide everything by that number. Here's my smallest number right here. Divide. I know that will give me a value of 1. Divide this. That gives me a value of 1.66785. Divide here. And finally here. Okay, looking at these numbers, in the past we have dealt with numbers that are so close to whole numbers we've just rounded. Well, if this is 2 1/3 and this is 1 2/3, I know to get rid of 1/3 or 2/3 I could multiply by 3 to get closer to a whole number. So let's try that. If I multiply by 3, now remember I have to multiply everything by 3, let's see what I get. I get 7 here, 5, 3, and 6. These are all whole numbers. That's my empirical formula. In this example, we had fractions. We took care of those fractions by multiplying everything by 3 to get whole numbers. What other fractions will you be likely to run into? Here are some examples. You might run into a fourth. This is the fraction form of this decimal. To get rid of a fourth, you'd simply multiply by 4 to get a whole number. If you run into something that's a third, you multiply by 3 to get a whole number. If you run into a half, you multiply by 2 to get a whole number. And when you have 2/3, you multiply by 3 to get a whole number.